thank you very much for being here. Thank you also for the invitation, Raphael. It's a pleasure to give this talk, also because of the fact that it's been a while since I've been to a physical conference, and it's a nice experience to have it again. My name is Giorgos Flouris, as you said, but I'm a principal researcher in FORTH, not very far from here, 2 hours drive from here. I work on, I'm a computer scientist. I used to work on belief revision a lot, not so much in the last few years, mostly on argumentation. That's why I chose this particular title for my talk, which consists of 2 components. The first half of it will be on belief revision, because, okay, this is the topic of the workshop. The second part will be on argumentation, which is something that's also one of the topics in the workshop and I've been working on for the last few years. And both of these topics are somehow put together under the umbrella of common sense reasoning in a sense that I will explain during my talk. So as you see, I chose PowerPoint for my slides, unlike most of the people in this Congress, explicitly because I wanted to discourage myself from using formulas. So I hope it will be easier for you to follow my presentation. So, what is common sense reasoning? Common sense reasoning, according to Wikipedia, is a human-like ability to make presumptions about the type and essence of ordinary situations that humans encounter every day. I would say, in a nutshell, common sense reasoning is the way to give your computer the ability to think like a 4-year-old child. So it's a way to give your computer the ability to do reasoning that we do every day without even understanding it. These things include problems that are related to common sense reasoning, include causality, action, and effect, being able to realize that, for example, if this laptop drops, it will break and it will probably not function again. Naive physics, like with concepts like space and time. Folk psychology, being able to understand when someone is mad, happy, unhappy, and so on and so forth. Reasoning about action and change, qualitative and plausible reasoning, and other aspects of reasoning like non-monotonic, divisible reasoning, handling exceptions, handling inconsistencies, and all this stuff. And it has many applications. Maybe the most important one is the human-robot interaction, because if you want a human to collaborate with a robot, the human will definitely expect that the robot will be able to understand basic things that the human finds obvious. So common sense reasoning is very important in this respect. So as I said, this talk is not about common sense reasoning. I don't claim to be an expert in common sense reasoning. As I said, I'm an expert in belief revision and argumentation. So this talk will consist of 2 parts. The first part will deal with belief revision mostly. The idea here, the common sense problem that's related to this part of the talk is being able to reason about actions, their effects. And the problem we will address in this context is how to perform belief revision when reasoning about actions and effects, how to allow automated agents to handle unexpected observations when these happen. And there are 2 references that describe this work. The second part deals with the common sense problem of handling exceptions, and in particular, handling exceptions during computational argumentation. In a way, I will explain how we could allow arguments to be partly accepted in the sense of being accepted but with exceptions. And again, this work has been presented in last year's SKY, and there is also, I will also give you some hints on some work that is yet unpublished, is still in preparation. We expect to publish it in the next few months, hopefully. So I will start with the first part. As I said, it's about performing belief revision when reasoning about actions and effects to allow automated agents to handle unexpected observations. So first of all, what is reasoning about actions? As I said, it's a necessary component of common sense reasoning, because you need to be able to understand, to reason, to be able to understand the effects of each action. And for this, the way to do this, we explicitly represent events and their effects using special languages that we call action languages. Here we focus on event calculus, which is probably the most popular one. Now, what is event calculus? Event calculus is a sorted first-order non-monotonic language with an explicit representation of time. So in the event calculus, we essentially have events which affect the value of fluence. Fluence represents the state of the world. And we also have time points which allow us to model the passage of time usually in a discrete manner. So we have time point 1, time point 2, time point 3, etc. There is also the common sense law of inertia, which means that things tend to persist unless they are affected by some event. So only events change the status of the world. And we also have circumscription on top of event calculus, so we don't have any unexpected events. Whatever is recorded as an event happens, whatever is not recorded has not happened. So it's a kind of a closed world assumption. There are many dialects of event calculus. I will say a few things on those dialects later because they will appear in some of the slides. But before that, I would like to give you an example to make you understand what event calculus is, for those of you who haven't heard about it. So it's the quite famous example, yellow shooting, it's called. It's about a turkey which gets shot and dies, you know, such story. Anyway, the point is that how can we model this example with the event calculus? First of all, we could say, we use the predicate holds up to state that a certain fluent is true at a certain time point. In this particular case, we state that the fluent alive, which means that the turkey is alive, is true at the time point 0. We also have a way to record the narrative, the events. So, for example, happens should, comma 1 means that the event should happen at time point 1. And then you have a way to record the effects of events. So this particular formula states that when someone loads a gun, the gun becomes loaded. Initiates is the predicate used for that. It states that when the event load happens, the truth value of the fluent loaded becomes true. And this happens at time point t, which means that it's true at any time point. It's not true only for certain time points, but whenever load happens, loaded will become true. We could also have conditional effects of events. So this particular formula says that when a turkey is shot by a loaded gun, the turkey dies. So the predicate terminates says that when the event should happens, alive becomes false. This is the second part of the formula, and maybe I can show it. Anyway, probably I cannot do that. Anyway, when the should happens, the fluent alive becomes false. But in order for this to happen, there is a precondition that the fluent loaded is true. And T here does not stand for true, it stands for time points. So this formula essentially is true for any time point. Whenever a shot happens and the gun is loaded at that specific time point, then alive will become false. Now, okay, so the question now is, what is the relation between event calculus and belief revision? Because event calculus, as you saw already, has a way to model change and changes that happen due to events. However, event calculus is dealing with an explicit representation of events. So, and there are pre-established rules for handling the changes that are caused by events, whereas belief revision copes with information dynamicity and allows us to handle misconceptions. So, for example, when an observation contradicts the predictions of a theory, then the theory is obviously has a problem, and only belief revision can get us out of this problem. Event calculus will simply collapse because the theory will get an inconsistent result. And this can be shown with the following example, again on the yellow shooting scenario. So suppose at the time point 0, the turkey is alive and the gun is loaded, so we know these things. At time point 1, a shot happens, and therefore, due to our axiom that says that whenever a loaded gun shoots, then the turkey will stop being alive, we expect that alive will be false at time point 2. But what if at time point 3 we observe that the Turkey is actually alive? Now this, very good for the Turkey happy ending, but not very good for the reasoner, because we have a contradiction here. We have the alive, which was predicted to be false, and now we know it's true. Something is wrong. How do we get out of this contradiction? And this is where belief revision comes into play, as also Raphael described in his opening talk in this workshop. So obviously something is wrong with the agent's beliefs, and we have 3 different options to right this wrong. The first one is to assume that the shot didn't really happen. So our observation, our experience about the fact that the event happened is not true. So we retract this experience and everything goes well. The second option is to assume that our initial beliefs were wrong. No, the gun was not loaded in the first place. Somehow there was a misconception on this respect. And the third option is to assume that our domain axiomatization is wrong. So maybe a shot doesn't necessarily terminate the fluent alive. Now, I will remove this last option because, as for reasons that we'll explain later, we assume that the domain axiomatization is always wrong, is always correct, sorry. This is done both for practical reasons, because it's easier, and we'll get into trouble if we assume that we can also change the domain axiomatization, but also for intuitive reasons, because usually the domain axiomatization is more reliable. It's done by experts, so it's more reliable than our sensors of the sensors that gave us the initial beliefs or the events that are happening. So the approach to solve this problem is, first of all, to define an operator for revising event calculus theories, and this is done in the standard, let's say, workflow that we do in belief revision, in most of the works in belief revision. First, we identify a set of principles, then we define the operator, and then we implement the operator. So what about the principles? Some of them were already mentioned by Raphael at the beginning. So the main principles that we have, the first 2 are adapted from belief revision. Consistency means that the end result must be consistent. I cannot, after I revise my beliefs, I cannot result into a knowledge base that is inconsistent, because then belief revision didn't actually do its job. The second principle that we follow is the primacy of new information. So we assume that the new information is always correct. Some could say that, okay, maybe the new information is less reliable than the old one. Okay, let's not get into this discussion. Let's assume that what we observe now we believe more in it than what we had observed some time points ago. So these are both hard constraints. There is also a soft constraint, which again comes from belief revision. It's the principle of minimal change, which is probably the most important principle in belief revision. It says that we trust the original beliefs to the extent that they do not contradict the observation. This means that we do not remove from our knowledge base anything unless we really have to do it. And so the end result should be as close as possible to the original beliefs. And in this particular work, the closeness is based on a preference relation that assesses the cost of its performed change in a way that I will explain in a later slide. However, we have also 2 more principles which are not in the belief revision, in the mainstream belief revision literature. They are specific to the event calculus. The first one is the persistence of background knowledge, which is what I already mentioned, by the way, that we will not allow any changes in the domain-independent and domain-dependent or domain-independent axioms. Only changes the narrative in the initial beliefs. And the second hard constraint that is specific to event calculus is the principle of disallowing proactive change. This means that whenever we make the changes can be made on any time point, but explicit changes will be restricted up to the sensing time. This makes sense because any change you make after the sensing time will not eventually resolve the contradiction. But more importantly, this principle states that the cost of effects, when we count the cost in a way that I will explain later, is assessed up to the sensing time. So we don't care about the consequences of this effect of these changes after the sensing time, because that would essentially create problem with infinite values, etc., because time goes forever. So very sketchy, the sketch of the solution. Let's assume that the red ball here is the current state, and the blue balls are the possible alternative states that we could have. Based on the hard constraints that I mentioned earlier, we remove all the states that do not satisfy the principle of consistency, for example, the principle of primacy of new information, and so on and so forth. And this leaves us with a subset of our original alternatives. These are called the revision candidates. Now, the revision candidates are then sorted based on the preference relation, and we find the closest one, which should be the result of our Billig revision operator. If there are more than one closest states, then we take them both with a disjunction. Now, this is, of course, if you get to the technical part, it's not that trivial. First of all, you must decide on what type of event calculus you talk about. So there are two basic cases here: the non-epistemic case, which is modeled by DEC, the DEC calculus, in which all fluents are known, either true or false. We don't have unknown fluents; it's a kind of closed word assumption. And also, we could optionally have default initial knowledge. So we could say that by default, I believe that this particular thing is true unless I have some other information in the beginning. This thing, I put it in green because it was essentially added to our theory after our first paper in the context of the second paper that I mentioned in the beginning. So in the non-epistemic case, the result is the cheapest revision candidate, but each one has one possible world because the fluents are, as I said, either true or false. And then we have the epistemic case, in which we also allow fluents to be unknown, and therefore we need additional predicates to model the fact that we may not know whether a certain fluent is true or not. Of course, we could add default initial knowledge as well, and again, the result is the cheapest revision candidate as before. And now I will explain how we choose the closest revision candidate that I mentioned earlier. The idea here is to use an arithmetic formula. We take a weighted sum of the cost of the explicit and implicit changes up to the time point of the observation. So we count the events that we decided to disbelieve are at. So events that actually we originally thought that they happened, but now we believe that they didn't. We have new events, events that we didn't believe that happened, but now we believe that they did. And then we have modified beliefs, which are those fluents for which the truth value changed from true to false or vice versa. We take a weight for each of those three different types of changes, we sum it, and that's the actual cost for each revision candidate. So then all you have to do is to compare using the standard arithmetic comparison. Of course, if we're talking about the epistemic case, in which we have also beliefs that are unknown, then we have to also consider beliefs which were unknown before and now they are known, or vice versa, known before, now unknown. And if we have default beliefs, we also have to consider a sixth category, modified default beliefs. And so this was the original approach. An alternative approach, which could be used alternatively, is to consider stratified preferences. This means that we order all those six types of changes, and we take the one, let's say, in our case, the more expensive one was the lost event. So everything, so if a certain knowledge base has more lost events than another, then by default it's gone, it's out. It's not considered because all others. So we first compare in the most expensive type, and if in case of equality we go to the lowest. Otherwise we just take a decision there. So this is a different way to model. It's a different type of preference, which could be useful in certain contexts. And also, we consider a linear function in which we degrade the cost over time, which means that all beliefs actually cost more than newer ones, in the sense that beliefs that we have had for a long time are considered more entrenched, more correct than the newer ones, and therefore we are less inclined to remove them or change them. Now implementation happened using answer set programming. Most of the work is done there. We also have a Java component which orchestrates the different answer set, the different reasoning tasks. We also performed a few optimizations. The relevant and irrelevant fluence goes as follows. We created a formal way to identify fluents that are definitely irrelevant to the situation that caused the inconsistency. And for these fluents, we don't even consider changing them due to the principle of minimal change. And this allows us to significantly reduce the search space and be more efficient. There's also a demo available in case anyone wants to visit in our website. This is the architecture. I will not go through it. I don't think it's very important for this audience, but very briefly, we take the events, any new event that comes, we check whether it's consistent or not using ASP, and then we have a meta program which essentially computes the revision candidates and the cost minimal revisions which are given to the Java parser to create the new knowledge base, and then we wait for the new observation to happen and move on. So this was part one. Now I'm going to the second part, in which I remind you that it's about handling exceptions in computational argumentation by allowing argument to be partly accepted, meaning accepted but with exceptions. So first of all, a few details about what's computational argumentation. Computational argumentation is somehow a descendant of rhetorics and formal argumentation, which attempt to model the dynamics of debate, self-deliberation, and other types of discussion between humans. Computational argumentation tries to do this, tries to model this in the computer science realm. So there have been a lot of pioneers on that since the 60s, 70s, 80s, but essentially the field is now largely based on the work that was performed by Dunk in 1995. Dunk made the following very simple but also very important, had the following very important idea. He said, instead of trying to understand how, what is the context of each argument and how the interaction between arguments happen, why don't we just forget about the internal structure of the arguments and just model the arguments themselves and their interrelationships? So what he said is, give me a graph. The nodes are the arguments. The edges are the attacks between them. And if you give me that, that's enough for me to decide which arguments are accepted, which arguments are rejected, and so on and so forth. So this very simple idea was very successful and led, as I said, to this to the emergence of the new field. Of course, then the question is, how do you decide which arguments are accepted and which arguments are rejected? The idea of Doom was that we have this notion of defense. So we choose a set of arguments, and if this set of arguments somehow protects itself from other attacks from outsiders, then this set of arguments is somehow accepted. And of course, the details differ depending on the exact type of semantics that you choose. So for example, in the admissible semantics, all the members of S must be defended by the members of S. So in the specific graph that you see in the bottom, A alone is admissible because its only member, A itself, is defended by A because only B attacks A and A also attacks B back, so it's okay. But it's not complete, because if you look at the definition of complete, it says that all members of S must be defended by S, but there should be no other defended arguments. Here, if you take A alone, you notice that also C is defended, because C is attacked by B and B is attacked by A, therefore A defends C. And therefore, A alone is not complete, but AC is complete. The exact details are not very important, so I will skip them for now. So what is our work? Our idea essentially adds a D, as you see here in the AAFs. This stands for domain assignments. And I think it's better to explain this with an example. So suppose that you have an apple, and for some reason you cannot see its color. Perhaps you're colorblind or somehow it's obscured from you, I don't know. So you have these two arguments. The first one says that all apples are red, therefore this apple is red. And the second argument says this apple is a Granny Smith apples are green, and therefore this apple is green. If you try to model this using standard argumentation frameworks, you will have something like this. Two arguments, A and B, B attacks A, and therefore, by the semantics that I showed earlier, B is the winner, A is the loser. We fully accept B, we don't accept A. However, there is a problem with that because A, in principle, it's correct. I mean, it's not a bad argument. However, maybe it doesn't apply for this particular apple. Maybe it applies for many other apples, but not for this particular one. And what we would like to say here is to somehow partially accept A. Partially accept in the sense of allowing exceptions. So it's not like accepting it with a certain percentage, accepting it by 60% or so on, or because this is a different class of semantics which have been addressed in other papers. Here we want to fully accept A for some apples and fully reject it for other apples. And to do that, the basic idea is that first we define a universe. A universe is a set of objects that we talk about, that our arguments talk about. Let's suppose that we have these 6 objects in our universe, these 6 elements. And then the ADFT graph is just a graph as before, except that the nodes now are not just dummy nodes, they're not just one letter, they are something a bit more complex. They contain elements. So argument B applies for 2 specific elements, number 1 and number 4. And argument A applies for 5 specific elements, number 1, 2, 3, 4, 5. Okay, so this is the main change here. And then to define the semantics, instead of dropping entirely an argument or accepting entirely an argument, we define semantics are defined through scopes. A scope is a function that determines the elements that remain in the domains after the attack. So in this particular scenario that I showed, argument B will attack argument A, but its attack is only relevant for the apples that argument B talks about, Granny Smith apples. Therefore, this is what will happen. We will just remove apple 1 and apple 4 from the domain of argument A, but we still retain our belief in argument A with regards to the other apples that it talks about. Now, based on this idea, we can define AFD semantics. They are very similar to AAF semantics. They are defined in the same manner, except that, as I explained earlier, we don't talk about arguments, we talk about scopes, we talk about elements inside arguments that are individually accepted or rejected. Not the arguments as a whole, but individual elements of the arguments are accepted or rejected. And if you read at the definitions here, you will see that they are a simple transliteration of the definition that I showed a couple of slides ago about AAF, so it's basically the same thing. The only exception is the last 2 ones, compliant and canonical, which don't appear in standard AAF. They don't make sense here. They make sense here. Compliant extensions or compliant scopes, if you like, require that the scope of an argument is a subset of its domain, meaning that you cannot, during the process of reasoning and manipulating your argumentation framework to decide what should be accepted and what should not be accepted, you should not somehow enhance your domain. Your argument talks about certain things. You cannot add new things to its domain during your reasoning. That's reasonable, I guess. And the second is the canonical elements, which I will explain in the next slide because they're a bit more complex. So the idea of canonical exceptions is based on the idea of indistinguishable elements. So if you notice the domains of the arguments A and B, you will see that apple 1 and apple 4 always go together, and apples 2, 3, 5 always go together. So based on this, we can define an equivalence relation that somehow partitions our universe into equivalence classes. In this case, one equivalence class is 1, 4, the other is 2, 3, 5, and the other one is 6 alone. And the idea here is that from the perspective of the modeler, apple 1 and apple 4, we do not have any reason to treat them differently. They are always in the same arguments, they receive the same attacks, and so on and so forth. If I put argument if I put apple 1 in a certain argument, in the scope of a certain argument, then I should put apple 4 in the same scope of the same argument. So that's what canonical extensions do. They essentially require you to have equal treatment to elements that are indistinguishable from the perspective of the model. And here are some results. This is the hierarchy. What you see here is the hierarchy of the different extensions that we defined. So stable extensions are also preferred extensions are also complete, and so on. The numbers show whether these extensions are guaranteed to exist. So as you see, all extensions are guaranteed to exist except stable ones. Grounded extensions are unique. Now these results are also true for the standard AEF, so the correspondence that I mentioned earlier still holds here. We don't have any surprises. Perhaps I should also give some extra mention to canonical elements, canonical extensions which do not exist in AEFs. As you see, there always exist canonical extensions. The interesting thing here is that canonical extensions are orthogonal to the other type. So, for example, you may have preferred extensions and preferred non-canonical extensions and preferred canonical extensions. You may have complete canonical extensions and complete non-canonical extensions, and so on. Importantly, if you can find a stable extension, which is not guaranteed always, then you can also find a stable canonical extension. For grounded, of course, which are unique, the only grounded extension is also a canonical one, so it's another interesting result here. Now, additional properties of AFD semantics are the following. Now, before we started defining the AFDs, we set some desiderata, and here I show you those desiderata and how the different scopes, which different scopes satisfy those desiderata. So one of them is that the final scope of an argument is a subset of its original domain. It's what I explained about compliance. It's satisfied by almost all types of scopes. The second one is that any reduction in the scope is justified on the basis of a relevant attack. This means that I cannot arbitrarily remove elements from the domain of an argument. I only do that when I have to, and this is kind of reminds of the principle of minimal change that I mentioned in the first part of my talk. And this is satisfied by not by some of the extensions that we define. The third one is that we should not allow overlaps among the scopes of arguments that are connected through an attack. This means that if I have two arguments, let's say A and B, and there's an attack between them, then and they have common elements. These common elements cannot appear in both. You either remove them from one or the other, or maybe from both, but you cannot keep them in both. And this is satisfied again by almost all our semantics. And finally, elements of the universe that belong to the same domain should also belong to the same scopes. Now this is tailor-made directly to the canonical extensions, and they distinguish some elements that I mentioned in the previous slide, so satisfied by the canonical extensions. Now, about the expressive power, so one would assume that AFDs are more expressive than AAFs because they have this extra thing about this domain, but in fact they are not. What they offer, these new features, what they offer is just convenience and design clarity. We can actually define mappings that reduce one to the other. Of course, to reduce AFDs to AFs, it's very simple. Just take the universe to be a singleton set. The opposite is not that trivial, but it's not very difficult. I will show it now. You can do it with what we call a natural mapping. So this is our original AFD. I will show you with an example. What you do is you take its argument and its element in its domain, and you create one argument in the AAF. So now we have 5 arguments for argument that are spawned for argument A, and 2 arguments that are spawned from argument B, and then you create the attacks accordingly, and this is your AAF. Now, if you take and compute the semantics of this AAF, then you can easily, from that, conclude the semantics of the AFD, and vice versa. And therefore, this shows the equivalence that I mentioned in the previous slide. There's also another way to do that, which takes into account the indistinguishable elements that I mentioned. So here you have these equivalence classes, and instead of creating one argument for each For each element, you create one argument for each equivalence class. So in this case, you have A14, you collapse those two elements together. A235, you collapse all those elements together. And again, you create the respective attacks, and that's your AF. Again, there is an easy reduction between the semantics of one to the semantics of the other, with one caveat that this AAF will only compute canonical extensions, it will not compute non-canonical extensions. So you may have noticed that the AAFs that result from the AFDs are larger, they have more nodes. This is normal. This is what you pay for the extra, for the fact that you have the domains in the AFDs. And our size in the worst case is for the natural mapping is quadratic to the number of arguments and number of elements, whereas in the second mapping with equivalences, it's exponential to the number of arguments, but interestingly, irrelevant to the universe size. So when you have a very large universe, a very large number of elements that your arguments talk about, then it is usually better to use the second mapping because it will be smaller, low exponential compared to the first one. Now we'll talk a bit about the future, some future extensions that we have conceived. This part is unpublished work, so I will not give many details, partly because we are not also ourselves very sure about them. But before I go to the future, let's look a bit to the past. In 2010, Prevka and Voltran defined what's called the abstract dialectical frameworks. The abstract dialectical frameworks change the AAFs by changing the semantics of the arrows. So if you recall, the arrows in the AAF indicate attack. The Prevka and Voltran said, no, why don't we make these edges represent any type of relationship among arguments? So instead of having attacks, the edges represent some kind of propositional formulas that determine whether an argument should be accepted or not based on whether the other arguments are accepted or not. So some examples of acceptance condition are accept A if B is accepted, accept A if either B or C is accepted, or accept A if B is not accepted and C is accepted. So any type of Boolean combination of arguments can form the acceptance condition of another argument. Sometimes you can also use the same argument in the acceptance condition of the argument itself, but this creates interesting things. Anyway, the point is that this is a direct generalization of AAFs and a very interesting one, a very important one. And what we thought is, why don't we use the same idea on ADFs? Now create the ADFDs, the abstract dialectical frameworks with the domain assignments again. The idea is the same. We put domain assignments to ADFs. We define a universe. And using this universe and an assignment of the elements to domains, we have essentially an ADF, but a bit more expressive. So this schema here shows the evolution. We started with AAFs. We had two orthogonal types of extensions, one with acceptance condition and one with domain assignments, and now we take them together to create the ADFDs. This idea means that the acceptance condition now can be first order logic formulas because you have also elements and arguments. And a few details on this. First of all, the domain of application of each argument. In the previous part of my talk, I said that we define this extensionally, so we explicitly say which elements appear in each argument. Here we can do it also intentionally, based on a certain language. For example, first order logic, we can say that the elements of A are all the Granny Smith apples, or the elements of A are all the males who spouse a doctor, or whatever you can think about. It's so you define in this way the elements that are in the domain of application of a certain argument, and then the acceptance condition are based on the same language plus the acceptance of other arguments. So examples will make it clearer. For example, accept a certain element U for a certain argument A when U is accepted for B. And this is expressed by the formula that you see in the brackets, B of U, a very simple first order logic formula with one free variable. The same can be done here, accept U for A when U is accepted for B and not accepted for C, or when U is accepted for D. Again, a very simple formula that with one free variable again that shows you whether U should be accepted for A, depending on whether it's accepted for B, C, and D. Of course, you can do stuff with other elements as well. You can use quantifiers. I don't have such an example here, but of course you can. For example, say that I accept U for A if there exists some U prime that is accepted for B or whatever. Here I have another example where you accept U for A when U is not accepted for B or when U prime is accepted for B. And of course you can combine also the elements of your language, your first order logic language, with the acceptance conditions. So accept U for A when U is an apple and not accepted for B. So this is written in the way that I showed here. And then to define semantics, you do it in a way analogous to AAFs. It's a bit more complex than the AAFs that I showed earlier because the acceptance conditions make it a bit more complex, but the idea is more or less the same. I will skip it for now because it would take like a while to do that. So, to sum up, I gave a brief summary of two different works that we have done with my team in FORTH, which both fall under the umbrella of common sense reasoning. The first part deals with the common sense problem of reasoning about action-based effects, and in particular, we explained how we can do belief revision on such languages. As far as we know, there have been no works that deal with belief revision on such languages. And the second part was about handling exceptions during computational argumentation. So we showed how we can make arguments be partly accepted and how we can formalize this idea. So that's all from my side. Thank you very much.
Thank you very much, Giorgos.